This particular problem, which is actually an easy problem, we are given a bunch of linear equations all over GF2. I should have mentioned this. All operations are happening in the same GF2, that is, we're doing mod 2 operations. There are a bunch of m linear equations, and you're asking if they're simultaneously satisfiable. This is an easy problem, of course, but what we'll show is, we'll show that there is an exponentially long proof which can be verified with a verifier which just takes n amount of time rather than mn time which the usual verifier would have taken. And we said with the classical NP witness would have been x, give the feasible assignment. Instead of that, we are going to be giving the Adamar encoding of x. What do I mean by that? The Adamar encoding of x is this object is. You're going to take a n-bit string and you're going to blow it up to 2n bits, exponentially long. And what is this exponentially long string? Every bit of this output, we are going to index it itself by a string of length n. So it's sort of taking x, and you're going to give the dot product of x with every possible y. So in some sense, it's the truth table evaluation of this function, L of x going from 0, 1, n to 0, 1, in which y is mapped to the dot product with xy. The Adamar encoding is the truth table of this particular function. And this is what we're going to expect as proof for this. So if some x satisfies it, we are going to expect the honest prover to provide this as the Adamar encoding of x, and we'll show that we can check this very locally to check if x were a valid witness to it. It can be, you can check it and be convinced with probability 1 that x satisfies all these equations. If there is no such x that satisfies all of them, no matter what you give, whether you give the Adamar encoding of some purported string x or just some other 2n-bit long string, if the verifier will catch it with constant probability, it will observe that this is not just. So let's see a couple of properties of the Adamar encoding. So Adamar encoding is, you're mapping x to sort of the truth table of this function L of x. Now the way we have defined L of x is this function that maps n bits to 1 bit, which maps a y to the dot product of xy. This is just shorthand for xi by I and then from n. Because it's a linear function, it has one, let's make one observation, it has this following property, that for all yz in 0, 1 to the n, Lx of y plus Lx of z is equal to Lx of y plus z. It has this property. So this property lets us, an immediate consequence of this property is the following. Suppose the following self-correction property. Suppose you're given some function f, and you know that it is close, and f is delta close Lx for some x. What I mean by that is probability over y, f of y not equal to Lx of y is less than delta. That is, this is a function which on most places it is actually equal to it, but it's possible, but you do not know that it possibly is not equal to f Lx at a few places, and you do not know which places. These places could have been chosen adversarially, and delta is some number, say strictly less than 1/4. Then you can actually recover, then for all z in 0, 1 to the n, you can actually, what's a candidate? This one, you can just look at the function f of x plus z, f of y plus z minus f of y. So for every point z, you want you're given a sort of corrupted version of L of x. You're not given L of x, but you sort of smudged delta fraction of it. But yet, you can sort of recover the exact value by sort of this local correction, because you know this is a random point. You just choose f of y plus z. This is a completely random point. This is a random point. So these 2 points are going to be going to be the right value with probability 1 minus delta each. So this, in fact, this is with probability 1 minus 2 delta. You have that you actually have recovered this. So even though you don't have access to the actual linear function, you have access only to some corrupted version of the linear function. It says with just 2 queries, you can actually recover the actual linear function from this corrupted value, as long as the corruptions are not too large. So this is one important property that we will use. This encoding has this feature. It has the self-correction. The other important feature which we'll use is sort of this. This is actually a characterization of Lx. So if a function satisfies this, let me write it down here. F is Lx for some x if and only if for all yz we have the property that f of y plus f of z equals f of y plus z. This is sort of a characterization of all the linear functions. It's not just a characterization, it's actually what we will see, what I'll write just now. It's a robust characterization. What do I mean by that? You can consider the following sort of. So somebody gives you this truth table f and they claim it's a linear function, and you want to check it's a linear function or not. If it's a linear function, we know it has to satisfy this property. So what one could do is actually pick a random yz and check if this property is satisfied. What we can show is if the function is far from linear, this test will actually be violated most of the time. If it is linear, of course, it's going to be satisfied all the time. That's what this saying is. The other thing is, if the function is far from linear, this test, it's just a 3-query test. It's an exponentially long table. If this function is far from being linear, just looking at 3 queries in it will tell you whether the function is close to being a linear function or not. So this test, which was proposed by Blum, Luby, and Rubenfeld, the following. It gets as input this function. Now it doesn't get to read the entire function. It's only going to probe it at a few locations. It wants to check if f is linear or not. It picks random yz from 0, 1 to n, probes f at y, z, and y plus z, and accepts if f of y plus z equals f of y plus f of z. Certainly we know that this test has the following, just the following factors. It has the following completeness property, that is, if f is linear, then probability that the BLR test accepts is 1. Non-trivial statement to prove, which requires, this is theorem due to BLR subsequent improvements, is the following fact: for all delta less than half, if the test accepts with probability greater than 1 minus delta, then in fact there is some linear function x such that f is delta close to Lx. So if this is, in that sense, it's a robust characterization. You can just probe this function at 3 locations and be convinced that it is actually, it might not be linear, but it is close to some being linear function. If it is far from linear, most of these tests are going to catch it. So if it's delta far, at least delta fraction of the tests will of these tests will sort of violate it. Delta fraction of these local views are going to observe that there is an inconsistency and what's given in this truth table is not a linear function. So we'll just use this. This is a non-trivial theorem to prove. We're going to assume this and complete the proof of our PCP construction. So we want to show what the new verifier for the system of linear equations does. So it expects as proof the some function f, which in the honest case is actually f is Lx, where x satisfies the linear equations. Verifier steps are good. We're going to have two types of tests. One is going to be, there are going to be a few syntactic tests in which it's just going to test if f is of the right type. Is it a linear function? And then it's going to check semantically whether the linear function it encodes is actually one that satisfies this one. So they're going to be, the tests are going to be of two types, syntactic tests and semantic. Yes. The syntactic test in this case, in fact, for the reason I'm writing it this way, even the subsequent verifiers I'm going to write are all going to have this part. There's going to be a first part of the test which is going to be syntactic. It's going to check if the encodings have some properties. And then second part is the encodings are encodings of NP witnesses that satisfy the original predicate. We're going to have this sort of two one. And in this case, the syntactic test is clear. It's just going to be run the BLR test, perform BLR test. Just do this. And at the end of this, if this test passes, we know that this function is close to some linear function. It might not be it is close to some Lx. This x need not satisfy all the linear function, but we know if this test passes over here, it is going to be close to some linear function. Now we need to check that x is actually satisfies all the linear functions. But now, and what do we know? Once it passes this part of the test, we know that f is close to a linear function. So we actually have access. Because if you have a function which is close to a linear function, we can actually produce the linear function by doing the self-correction. So at this point, once the test passes this, we can do self-correction to obtain the value of L of x at any point we want to. Ideally, we would have liked to check all these places. So we could have queried L of x at A1, L of x at A2, L of x at AM, and the answers were B1 to BM, we would be done. But this is sort of wasteful in the sense you're doing M operations anyway here. I want to say you can do something even better. So what we will do is we'll do the following fact. We will pick M random bits and construct this vector A, which is just the addition of the M of those n vectors. It's going to be some addition of this one. You're going to pick, basically, for every AI, you're tossing a random coin and asking whether I'm going to include it or not, and so on. And it's going to take the corresponding addition. And what we want, so this is an easy fact it's easy to check. If x satisfies all M equations, then A of x, which is Lx of A, is in fact equal to summation epsilon I bi. Otherwise, the probability that Lx of A equal to epsilon bi over the choices of epsilon 1 to epsilon n is less than or equal to half. This is just a consequence. These are two different linear functions. If they are not the same linear function, they have to disagree on at least half the locations. It's much simpler than the Schwarz-Zippel lemma, but this is just a consequence of the Schwarz-Zippel lemma. So we'll just use this. So we will use this. We would like to query the function at A, but we can't query A might be a corrupted location, so we'll use self-correction. So we'll pick another completely random this one, and we will check we'll look at f of a plus a prime minus f of a prime is equal to summation epsilon I b. Except if that's not. And this will check with probability half, you will reject if if the x that was close to this did not satisfy it, you will reject it. Otherwise, you will pass this test. So this is the entire proof of it. It queries the test only at, if you notice it, exactly 5 locations. At 5 locations, you query it at 5 locations. It's an exponentially long proof. That's a caveat of this. But querying it at 5 locations, and the verifier extremely efficient. It's able to check that this encoding is actually close. This encoding proves that these things are simultaneously satisfiable.
Yeah. Sorry, probably a dumb question, but I'm still stuck on the self-correction. It looks like you're taking something that's good with probability 1 minus delta, and you're turning it into something that's good with probability 1 minus 2 delta.
No. So it is good with probability 1 minus delta at a random point. This is for every point I'm going to get. So you know at a random point, f of y is equal to L of xy. But I want it to be correct at a point of my choice. So it need not be. So they're saying for my point, I'll use 2 points, both of which are random, and be able to recover it. So it's going from average case to worst case. Gotcha. And the fact is you can do it with the Adama encoding is powerful enough to let you do it with just 2 queries.
They're not independently random. Does that not matter?
Yeah, I'm just doing the union bound over here. That's why it's a 2 delta. They're not independent, but this is just union bound, so it's okay. Question. So this is the 5 query proof for this one. You're using the power of polynomials, rather just degree 1 polynomials, and the fact that they have this amazing local testability property over here.
So the 5 are the 3 from the VLR, the 2 from down there. But what is this BIS? I'm sorry.
So the test was trying to check these linear equations. It's the right hand side of the linear equations. Yeah. So it's just checking.
And the epsilons are 0, 1s.
Epsilons are random 0, 1s. It's just a random linear combination of. Yeah, so that does it for this system, which was an easy problem. Now you can ask this, how do we modify this when these were not linear equations, but quadratic equations? Want of time, I'm not going to go into the details. I'll quickly tell. So the way the Hadamard encoding is viewed, so the way we have viewed it is over here, the Hadamard encoding has 2 possible interpretations. The interpretation over here which we have used is, it is the evaluation of the linear function Lx at all points y 0, 1 to the n. But because of the symmetry of x and y, this can also be viewed as it's the evaluation of all linear functions Ly at the point x. It has this, because of the symmetry of the way x and y are this one, it has this interpretation. So to handle quadratic things, instead of working with, the way we will give the encoding of x is we'll give evaluation of all quadratic functions at the point x, and that has a similar such test, which is actually just taking the BLR test and sort of souping it up with the Free-Walls algorithm, which Justin had mentioned in the morning. We'll use that, and that will give you a quadratic test, and then you do the same thing over there. For want of time, I'm going to skip it. It has no extra The main things are this fact. The heart of the proof is the fact of both these tests is the fact that the Hadamard encoding is linearly testable. You can test Hadamard encoding, the fact that something is close to Hadamard encoding by just looking at 3 bits. And that's the main thing. It's this fact, the soundness of this test. This is a non-trivial statement. And given this, we are able to construct this 5-query test for this one. Yeah, so that's the conclusion of the first part of what I wanted to show. This will show that NP is contained in PCP some probability over here, say 9, 10 or in this case it was order n, but when you go to quadratic it will be order n square. The number of random bits, basically these are the The random bits are n over here and another n over here, and some 5. This 5 in the quadratic case, I think, becomes some 12 or something. Okay. Any questions on this? So even this, of course, the issue over here is that the proof is exponentially long. It's, in the case of linear thing, it's 2 power n long. In the case of quadratic, it will be 2 power n square long. But the amazing fact is you could just look at some constant locations, number of locations, 12 locations, and be convinced that there is an x that satisfies all the response. It's saying, and says that if there is no x, a good fraction, that is 1/10 of the local views are going to observe the inconsistency. So you're sort of smearing the inconsistency all over the proof. It's the same thing that's happening to polynomials. If two polynomials are distinct, they're distinct almost everywhere. Here, if the proof is false, there is no, if the theorem were, if there is no x that satisfies all the equations, there is no way you could come up with one single proof which satisfies most of the things. You're going to have errors all over the place. It's sort of throwing with the errors, and the heart of the proof is the testability of the Adamar encoding, the Blum-Lobe-Rubenfeld test. Any questions so far? We'll now see how to modify this to reduce the randomness or to make the proof shorter. The proof is exponentially long, we would want to make it polynomially long.
What is the sumness you get there?
You have to do a careful analysis of BLR and this one. It will be some constant bounded away from 1. Yeah. So given that I'm not worrying about this constant, you can boost that with this. Yeah. So you can get any constant you want to over there. So what we would now want to do is we want to sort of soup the system up to get it to make the proof shorter. For the sake of presentation, I'm going to work with a different NP-complete problem. You could work with any NP-complete problem which can be arithmetized nicely, but we will change the NP. Here, like I've just worked with system of quadratic equations, I'll work with graph coloring, and that will be most convenient. But it's not a feature of we could work with any problem over here. So the next part which I'm going to show is part 2 is polynomial sized PCPs. So it will be great with respect to size. However, we'll get only polylogarithmic query complexity. This is also quite, I think it's not what I had promised constant, but this is also something you're looking at the proof at a very few locations and you'll be still convinced. Polylogarithmic. And the problem we'll be working with is tree coloring. We're given a graph. We'll think of the edges being given as V cross V. We'll say which pairs of vertices are edges. Assume it's a symmetric function. The question I want to ask is, does there exist a coloring? Does there exist a proper tree coloring? Such that every edge problem ask, and we will show. So the class, once again, the classical NP witness for this is the tree coloring itself. Is the tree coloring if one exists. And what we now show is what is going to be the PCP proof, the PCP proof of this. Once again, it's going to be some encoding of the coloring, which is also going to take the graph into account. which can be very locally checked. It's good. The encoding is going to be only polynomially long, unlike before. It's going to be polynomially long, but which you can check with just looking at the proof at just polylogarithmic number of locations. That's what we will do now. Sort of going to be motivated by this example. So what did we have here? We had this function which was, what was this? So the Adamad encoding was low. The heart of the proof was the fact that the Adamad encoding is locally testable. That is, you could check if some function is close to being a linear function or not by just looking at it at a few locations. This was crucial in getting down, in ensuring that the encoding had a nice syntactic property, and once it was syntactic, the semantic property could be done. So we want a similar such thing. We want some encoding in which you can check that the fact it's an encoding, it's a valid encoding very quickly, and then we'll somehow use somehow map the semantics into the problem to check this other part. So what we want is a corresponding this one over here. This was checking whether a given linear function is linear or not is locally testable. Natural generalization is, I'm not going to talk about linear functions, but low degree functions. I'm going to talk about some low function, and we have a table which is supposedly an evaluation of a low degree function. Can we check if it is low degree or not? And we'll see if that actually show that that is actually going to work for this. So we're going to talk about following. We're going to work with some field S, space Q, and some degree parameter D. Take of D significantly smaller than Q. Q is large enough, this one, so that we can apply Schwarzschild. And we'll look at it as an M variate function. P, when you write it as a polynomial, in other words, P can be written as the variables. It has a unique, you write it as some AM, AI1, I2, IM, X1, I1, Xm, IM. All the monomials have degree at less than or equal to D. We'll look at these functions, the class of functions. Previously, we were looking at Adamad encoding, which is class of all linear functions. We'll look at class of all this one. These are what are going to be called. This is the Reed-Muller code.
The degree less than D is the total degree?
This is the total degree. Yeah. And as before, we are going to use the fact that if you are given two different Reed-Muller codes, P and Q are two different Reed-Muller codes. If you pick a random point, if they are the same Reed-Muller code, of course they will be equal everywhere. If you pick it, if they are distinct Reed-Muller code, distinct low degree polynomials, then almost at every point they will be the probability that they will be the same is very small. This is why we need the field size to be considerably larger than D. We choose such a setting of parameters. So Reed-Muller has this feature. It has this thing once again that two things are very distinct from each other, but we want to ask if it also has a similar local testability feature. That is, the BLR, the linear set of linear functions had this nice property. It had a very local characterization. That is, f is linear if and only if this three-query test passed, and furthermore, if this three-query test passes most of the time, then f is actually close to being linear. We want a similar such property for. Question is there a local test? For Reed-Muller codes. So that's actually a picture. So what do we have here? We are given some function f on this space. So think of this as f to the m. And you're given some function, a truth table of some function. So for every point, with this you are given an evaluation of f, and I want to check is f actually low degree or not. There's a very natural test one that suggests if f is, for this setting of parameters, d is larger than, if f is this parameter, you just pick a random line in this, random affine line in this space, and just look at the restriction of f to this line. That will be also a low degree function, a univariate low degree function. In fact, you can say that f is in Reed-Muller QMD. This is for certain setting of parameters. This is certain MDQ. The following is true. This is in fact a complete characterization. That is, f restricted to L is RMQ1D, the one variate version of it for all lines L. This is, you're able to check that this truth table, you're giving a truth table in f to the m values by just looking at, this is q to the m values, by just looking at q values, this is sort of a characterization of it. The question is this also a robust characterization? Just as this was a robust characterization for checking if something is linear, if this test passes most of the time, when then we knew that this is close to being linear, what we would like to know is if this test passes most of the time, is this being close to Reed-Muller code? And in fact, that is true. This is the low degree test. So the input here is pick a random affine line. Query f on L, accept f restricted to L is a univariate polynomial of degree less than or equal to. So certainly it has the completeness property. If f were a low degree function, then it's going to pass the test with probability 1. The amazing thing, which is certainly completely non-trivial to show, is if actually the test passes with probability 1 minus delta, then f is actually order delta close to being low degree. So the soundness, let me write it over here. The soundness of the low degree test. I think that there exists some delta naught or delta less than delta naught. If the probability of the low degree test accepting is greater than 1 minus delta, then then there exists a polynomial P in Rm QMD such that that is delta close.
Actual delta?
No, sorry, order delta.
And is there any dependence on the degree d?
So this delta naught is going to be, its delta naught is some function of the form m power a, d power b, q power c for a, b, c being universal constants. Therefore, we will just choose them. We'll choose md and q such that that is a fixed constant, and you'll have to choose a large enough field so that this is small, and yeah.
How do you check if f restricted to L is a univariate polynomial?
This is just, you do interpolation. It's just, so it's, but it's interpolation on a much smaller, it's not the whole space, it's a smaller space. Notice that this is sublinear even when m is 2 or so also, you are checking, and there are something like n square points, but just looking at n points you're able to check if this one. So it's you're able to check something by querying it at a very few locations, much smaller than the whole length, which is the spirit of what PCP is. You want to check the proof is valid by looking at much fewer locations than the entire proof. Any more questions? So this is going to be sort of the technical core. Just like we're going to replace the syntactic test, we're going to give, just like previously we had given the proof was the Hadamard encoding of The X, the proof is, now the new proof is going to be something else. It's going to be some Reed-Muller encodings of some functions related to the coloring. And the syntactic test is just basically going to check that all these functions are actually low degree functions. We will just do this low degree function for all of them. And then we will do some set of semantic tests to check that those low degree functions, the low degree functions which are close to the proofs actually are encodings of things which are valid 3 colorings.
There's something counterintuitive about the formula for delta naught.
Yeah, this is,
Is it the case that
no, this formula is wrong over here. This one, I think there might be a 1 minus going on over there. So let me make it a function of this and leave it.
yeah.
From delta naught function. Yeah, when I wrote it itself, I realized I was hoping nobody would catch me.
Question.
Yeah.
So in this step 3 down there, how do you check that it's low degree?
So the univariate case, so univariate, you just have q points. You want to check something is q points is variable. You take the first d points or d plus 1 points, interpolate to get the polynomial and check that the remaining q minus d plus 1 points have same value. Or that's one easy way of doing it. You could do any other. Okay.
So related to that, what does it mean to query F bold L?
So you query f on all the points along the line L. So f is given as a truth table, and you want to check that this f is actually, so for every point in f to the m, you are given the value of f. And you want to check that this truth, you want to look at this truth table but not read it entirety and be convinced that it is actually close to being low degree. So we will probe it only at locations along the line L. We pick a random line L in the space and probe it along the random line.
But you want to only read log n.
Huh? So for a certain setting of so we will set m to be such that the relation between q and f to the m will be log n, will be polylog n. So depending on how much time I have, I'll do this parameter setting. Eventually, the polylog n, the query complexity over here, is going to come from the fact that a line is going to be polylogarithmically smaller than the entire space.
But you have to query on the whole line.
I'll have to query on the whole line.
So the query complexity is f.
It's going to be, there are going to be several Reed-Muller codes that are going to be, so it will be some constant times f is going to be.
But just for the
Just for this, it's f. Yeah, but so it's not in the bit complexity world, it's f, in which each query itself is a field element. Any other questions? So what do we want to check? We want to check that there exists a coloring C on the vertices such that which is a proper 3 coloring. Because we're working with polynomials, I'm going to state this proper 3 coloring, this fact in a polynomial fashion. So we notice we had this edges. Edges was a function v cross v to 0, 1, which it's 1 if the edge is there and 0 otherwise. So this is equivalent to stating, this statement is equivalent to stating, if you look at the edge ij, so you want ai minus aj, ci minus cj should never be 0. It should be 1, 2, minus 1, minus 2. So we're just going to check this fact, minus 1. This should be 0 for all ij in v cross v. So either the edge is absent or if the edge is present, then at least the colors should be distinct. This sort of captures the fact it's a 3 coloring. So we want a C which has this property. Furthermore, so C should also be, because eventually we're going to be sort of taking low degree extensions of the C is going to be a function from V to 0, 1, 2. We're going to push V to F. So we also want to say C is actually is a 3 coloring. So this will be one condition. This is condition 1. The other condition we'll check is actually C has the property that for every vertex it gives one of these three values. So if there is a C which satisfies both these properties, we are done. So what we'll do is we will not, instead of giving C, we are going to give some polynomials related to C. In particular, we are going to give the sort of the low degree extension of C in a particular cleverly chosen fashion, which will help us to check these two properties extremely fast. So this is where the arithmetization is going to come. So now we're going to arithmetize the problem. So far it has all been on the original space. So we have the space f to the m. So we somehow have to move from the vertex space. The function, the domain of the functions are v. We want to move the domain being f to the m. So the way we will sort of do this is we'll pick some s, which is a subset of f. Look at the smaller subcube of f to the m. We're going to look at this smaller subcube of f to the m with the property that we will identify Sm in some canonical fashion with a set of vertices. So V is going to, S to the m is going to be, it's just the alternate labeling of the vertices. This is going to be of the same size as the vertices, some canonical fashion. We're going to do this. So now we can view the functions C as a function from S to the m to f and E as a function from Sm cross Sm to f given. Once we do this identification, we can view them this way. And now we will do what the low degree extension which Justin was talking. We will extend these functions. Right now these functions are defined only on this subcube. We will sort of extend it to the whole space. So we will talk of, this is the sort of the low degree extension. We are going to talk about a capital C going from f to the m to f. Let's call it C hat and E hat. Going from f to the 2m f such that C hat when restricted to hm and Sm is identical to C and E hat when restricted to S2m is identical to E. We're going to think of some extension of this function, but maintaining low degreeness. So this can always be done such that the degree of C hat and the degree of E hat is at most mod s in each variable. This is not hard to check. It's doable in the univariate case. So if you have a function, if you're given a function only on s locations and you want to extend it to f locations, there exists a degree s function. I'm sort of stating the same thing for the multivariate version. So we're going to ask us proofs C hat and E hat. The E hat is something the verifier has. The verifier can compute it itself. C hat the verifier does not have. The C hat is what the verifier is going to expect as proof. So the proof is going to be, there are going to be several parts of the proof. Certainly one is going to be this function C hat from f to the m to f. We can check its low degree, but we will have to give some more additional information to check that C hat satisfies these two properties. People with me so far? So we want to show that C is a valid 3 coloring. So instead of giving C, we are going to give the low degree extension of C, just like over there we gave the Hadamard encoding. And then we need to give some additional information to show that C hat satisfies these properties. What's additional information I'm going to give? So I want to check that this is true. So I'm going to give another function. So let's call this C1 is C1, and C1 in the honest case should be equal to C hat. And C2 is going to be just is just going to be the function which is just Cx minus 1 and Cx minus 2. It's going to be this low degree function. So I'm going to expect as proof even the second function going from f to the m to f. I'm going to give this. And what we need to now check, we need to check C2 restricted to Sm is identically 0. Rather, not C2, but the polynomial that C2 is close to is identically 0 on S to the m. Okay?
And the relation between C1 and C2.
And the relation between C1 and C2. But that actually is an easy thing to do if I'll come to that. This is just a polynomial identity. So if you check it at a random point, if they are true everywhere. So we will expect as a one table for C1, another table for C2, and then we're going to check that these. And now we're going to do the same thing. We're going to check, we're going to ask as another table B, which is just going to be E hat of ij, E hat of xy, and this complicated expression which I have, Cx minus Cy minus 1. This function, we'll ask this function. So this is also going to be, we're going to ask B going from f2m to f. This, and we also now we need to check that B on S2m is identically 0. So at this point, what are we doing? So that's this. The verifier is going to perform as before. It's going to perform some syntactic tests. It's going to basically perform low degree test on C1, C2, and B to be convinced that they are all, even if they are not low degree, they are close to being low degree. And then it's going to do some bunch of semantic tests. The semantic test will come of two types. One is, we'll have to check what Amit asked. We'll have to check that C2 has been derived properly from C1, B has been derived properly from C2, but these are all polynomial identities, so it's sufficient to check them at a random point. So we'll just, this is just checking if C2 and B have been obtained correctly. Just check at a random location. If they were different, they would, because at this point, if this test is passed, you're convinced that they are close to a random, they are close to a low degree function. Therefore, if they were low degree, then at a random location, they have to be, if they pass the identity, they have to satisfy the identity at every location. And if they are not satisfy the identity, they have to violate the identity at most locations. So this is fine. We need to still do these two tests. So that's the last semantic property. Just we didn't check that the low degree function, low degree polynomial close to C2 and also B is identically 0 on Sm and similarly S2 to the m. That's one last thing to do, and if you're done with that, we will pass the. So how do we check this? We are now going to, final property, we need to check you're given some function, you're given a low degree polynomial, and you want to check it's identically 0 on a subcube. One natural thing is pick a random point and check 0. But this is actually this one, because we have to check it is 0 everywhere. It might be true that it is 0 everywhere except one location, and that's enough to violate it being a non-3 color. We need to check that it is 0 completely in the space. But we need to do it by looking at, not by querying this entire table, but by querying very small number of locations. How does one do this? This is sort of inspired by the sum check, but it's going to be much simpler than the sum check protocol. Let's ask the univariate version of this problem. Yeah? What?
Just to ground it a little bit to some people. Why don't you, like, for a second connect it to the 3 color? So you're checking.
So let me tell what all has happened so far. So what all has happened? So we need to check that there is a, check that there is a coloring which is a valid 3 coloring. And we saw that something is a valid 3 coloring if it had we need to check there exists a C that satisfies 2 properties. One is, it is actually gives, for every vertex it gives only one of these 3 coloring, that Ci into Ci minus 1 into Ci minus 2 is 0. And the other is this test which I had just erased. Eij, that is, for every edge, the 2 colors provided are distinct colors. We need to check this. So what we instead do is we're not going to, the C is not going to be provided in its natural format, but in the low degree encoding of it. So instead of, we identify the vertex set with some subcube of this large space. So this is f to the m. We're identifying it with some subcube, and instead of providing C in just the subcube, we are going to provide the low degree function that is an extension of the subcube. At least we expect the prover to provide this. The prover could cheat and provide something else. So C1, the first part of the proof in the honest case should be the low degree extension of C. And now we need to check that this it's a low degree extension of some coloring which satisfies these 2 properties. So for that you also give the corresponding low degree extensions of those 2 polynomials. So C2 is the polynomial which is just got as C of x minus 1, C of x minus 2. We asked the prover to provide that function also, and also the function, the low degree function corresponding to this. So the prover is going to provide all these 3 low degree.
So the description of these functions, how long is it?
The truth table. So it's each of them, the eventual parameters will be, everything will be, right now it's going to be linear in f to the m, and we will be setting the field size in m such that this is poly in n eventually. So I don't know if I'll come to that. So eventual will be qm will be set to be equal to poly n, and q will be something like poly log n, m will be log n by log n. This will satisfy those parameters. Yeah. So the prover is going to provide these 3 tables. Now we need to check that these 3 tables are correct. That is, we can check that the low degreeness using the low degree test. We checked it. We need to check C2 has been obtained correctly from C1. Just check it at a random point. These are low. Now that you're convinced they are low degree functions, checking at a random point, you're guaranteed that C2 is in fact precisely this low degree function.
There should be hats over there, right?
Oh, this should be hats. That's the same thing.
What if E is identically 0?
Huh?
What if E, like, I mean, in that, don't we have to check the edge corresponds to the graph I have in hand?
No, but E is something the verifier can compute itself. So this part of it, it's going to compute this one, and these 3 it's going to pull out. So it's going to check this random location. E is something E hat is something the verifier can compute of its own, and C hat is going to read from the other table and check. So it's going to check the B is being given correctly by checking this polynomial identity. So at this point, we have come to a place where we know that the tables that we have are in fact low degree polynomials, and they have been obtained correctly from each other. What we do not know is that they are low degree extensions of functions that satisfies these 2 identities. So we need to check that C2, the low degree polynomial close to C2, is identical on S to the m. And similarly for B, let's just one of them. So, let's look at the univariate version of this, and you'll see there's an immediate.
And it's not the case that it's 0.
It's not the case that it is 0 everywhere, because certainly C2 is not 0 everywhere. It could be 0 everywhere. It could so happen C1. The only low degree extension of this possible is being 0 everywhere, but we need to check that. And notice the natural test of just picking a random, you have these polynomials, checking them at a random point here, checking if it is 0 is not good, because this could be just that it could not be 0 at one place, and it's impossible to do it by random query.
One way to see it is that C2 has degree that is higher than the minimum of the degree extension.
Yeah. If you query the entire thing, you're basically querying all the vertex, which is the same thing as the original NP witness. You want to do something much better.
But if it was 0 everywhere, then you could see.
If it was 0 everywhere, then you could have done, but we don't know if it is 0 everywhere. Yeah. Yeah, so simple observation in the univariate setting is the following thing. Suppose P is a function from F to F of degree less than or equal to D, and P happens to be identically 0 on S. What can you say about P? Then this must be true that P is in fact as a polynomial equivalent to the polynomial that is, we can say that if you look at this polynomial ZS, which is a polynomial that vanishes on S.
Q is a little bit overloaded here.
Okay, that may not use Q, there is S is S. Then there exists a polynomial P prime of degree D minus size of S, such that this happens. P is equal to ZS times P prime. The only way this can happen in the univariate setting is if ZS is a factor of P. So to prove that P is identically 0 on S, what I could give proof P prime and then check this polynomial identity. So you could give us proof to this, a proof that P is identically 0 on S is actually P prime of degree D minus size S, and then check the polynomial identity. P equals ZS P prime at a random location. If you do that, then this is true in the univariate setting. How do we do it in the multivariate setting? This natural extension for this, we'll write theorem over here and we'll be done with it. Given P f to the m f of degree less than or equal to D, P is identically 0 on the subcube if and only if there exist polynomials, what I call them, let's call them D1 up to Dm of degree less than or equal to D. They are actually even smaller degree, but this is good enough for me. So that P is identically the polynomial ZH xi into Di
Yes. Yes.
ZS. This is just the multivariate extension of the same statement. There I said that P is equal to the product of ZS and P prime. Here P will be equal to some summation of this form. It's clear if it's of this form, then P is identically equal to 0. The other part is also not hard to prove. It's just do repeated division m times and be just divide P by ZX x1, then divide P, then the remainder polynomial has to be identically 0. It's just this. So to show that P is identically 0 in Sm, the proof is going to be polynomials D1, D2, Dm. So we're going to give these as extra proofs. So proof is For this one, it's going to have a set of polynomials d1, d2, dm. And this one is going to have another set of polynomials f1, f2, fm. Syntactically, you check all of these are low degree polynomials. And then the last one, you check that for C2, so C2 at a random point x is equal to summation zhxi into di of x for a random x. And that's it. So you're convinced that if you give me all of these proof tables, there are about order m of them, which blows up the proof by a log m factor. This whole long proof actually encodes a satisfying a valid 3 coloring of the. And notice it, you're querying the proof only on certain lines, certain m lines is all that's been happening, order m lines. That's the worst complexity. And you set the parameters, you will get that this gives you a polylog. You can check that this actually says 3 coloring is in PCP sum 1, sum 99 over 100, order log n. I'll tell you why we have the order log n, polylog n. The order log n comes from you need to pick a random line or a random point space. How much is, it has been set such that qm is poly n. So random point or random line is going to be picking log n randomness. And yeah, at this point I think let's not go into the parameters, just setting this. Actually, for any setting of m, it's actually going to give you a non-trivial PCP theorem. It's going to say that you can query a proof of length, some proof in say n root n locations. It's sufficient. You can, if you set m to be like 5 or 6, you'll get that you're querying able to query a proof of length n in just square root n locations and be convinced of its veracity. If you set these parameters, you'll go down all the way to polylog n. And yeah, this.
And so the running time of the verifier, first you have to set up this e hat.
Yes, so e hat.
Take a poly at a time.
Yes.
And then after that, everything is efficient, right?
Modulo 1. So e hat. So in the case of coloring, it has to do e hat. That's an expensive thing. But for most problems, if the e hat, the typical arithmetization is done such that e is, if you can use the sort of succinct circuit format in which given e, you can arithmetize it and get this also efficiently. So the hard part is not e actually in this. The hard part is computing zhxi. It has to also compute zhxi.
Oh.
That happens to be an intensive task.
Wait, but I thought this is like, can't you make S? Yeah, S is very small, right? The size.
So we can actually, it happens to, okay, for actually this polylog n setting, it might be, no, this setting, it will be this one, it's fine.
You give me 2, right?
Yeah, this is fine.
So maybe I'm lost here, but why can't you do this like random linear combination like you did with the Reed-Muller instead of doing the division? Like when you want to check those.
Random linear combination of what?
On the points on S.
Like a random.
No, there you had random linear combination. How do I don't see how to do a random linear combination of. Randomly, I need to evaluate the function. There we interpreted the fact that given x, the Hadamard encoding gave every linear function on x. Therefore, a random linear function was also a linear function. Now, a random, this one might not be something. We don't have x. We don't have the coloring at every low degree. We don't have every low degree polynomial's evaluation at x. So Hadamard had these two properties.
The original version uses some check, right? The original version.
The original version used some check. This is a cleaner version too. It's the same thing as some check said in a much more succinct fashion.
Is it this equivalent between E and Z and the D polynomial? Does
Yes.
this hold over S or does this hold?
No, this is a polynomial identity.
Okay.
Just like over here, it's a polynomial identity. If P is identically 0 on S, this has to be an identity. The ZS should be a factor of this. It should hold. Therefore, this polynomial identity, as this is true for all. If you apply alpha, it's true at every alpha. And the same thing is true. It's a polynomial identity. Therefore, it's true. Either it's true everywhere or it's false at most locations. Because all the things.
Does it have to give DIs? Like,
Huh?
Approver does not have to give.
Yeah, no, it is giving.
So up there in the syntax.
Yeah, so there will be a whole bunch of, everything is going to be added over there. F1s, F1.
Okay, F1 through FM is for the B.
For the B's, yes.
Just make sure I understand correctly, the polynomial Z is a fixed polynomial.
The polynomial Z is a fixed polynomial.
Polynomial in the sky is over here in the box.
Yes. It's a fixed polynomial in this. Yeah. You can make that also efficiently. Actually, it's done in some of the works in which if you choose S to be not, right now S was an arbitrary set. If you had chosen S to be a subgroup, then Z will have it will have very few non-zero coefficients. And you can make Z, that also so extremely efficient. And that's used in trying to get the verifiers even more efficient than fake cross.
This maybe it's a trivial question, but this lemma do you have to prove some robust version of this lemma?
No, you don't have to prove any robust. This lemma has nothing to do with low degree. It says if you're given already a low degree polynomial.
Right, but the thing is that you only know that D1 up to Dn is close to.
Yeah, but you're checking it at a random location. Therefore, it's fine. Once you know it's close, you can. If you're checking it at a random location, it's once it passes this test. In the case of Hadamard, we had to query it.
So Schwarzschild is sort of an automatic, robust version of all such.
Yeah, Schwarzschild is an automatic robust version. Once you pass this, all polynomial identities become robust because of Schwarzschild. Yeah.
Okay. Good place to stop and thank Prahladh.